rest of the signal that's not supposed to be there that's there. So it depends on application. If you want a very precise identification of the periodicity within a signal, rectangular window is the one to go. If you are more into understanding, okay, oh, what is I want my spectrum to look so clean, okay, then you use Hamming window so to kill off the rest of the stuff. Okay, so it's a choice, and nobody knows the right answer. Here's simulated, right? So, but in real life, you don't have this simulated data. You have this as a speech recording noisy condition and try to process it. So that's the part. So if you look at an actual signal, so looking something like this. This is the time signal R, okay, with some local pitch variation measured at about 110 hertz. Okay, so again, BCD, they're rectangular window, Hamming window, different length. This is 30 milliseconds, this is 15 milliseconds. The longer it is, supposed to get the right the manual width is smaller. Compared to top and bottom, what you see supposed to see is a flatter spectrum because the non-noisy condition is there. So in a shorter segment, you get less oscillations. Okay, so we can again see all these things. Okay, when you see the real world picture, it's not as simple as that simple oscillation. Okay, 30 millisecond rectangular window, 110 hertz. Yeah, somewhat here. Yeah, you do see a peak here, but this one or this one, definitely not that one, right? Or this one. It's very hard to guess. Okay, but probably somewhere here you say there's some pitch. Okay, that's happened the first peak here, probably around 100 hertz. Okay, you're somewhat okay. If you get 15 millisecond window, yes, you still can get that kind of stuff. Okay. If you look at the Hamming window, which is this Hamming window, you still get this. Okay. If you look at a shorter rectangular window, then you still have that, but the window width gets larger, so you get less precise in this value versus here, right? Because you have a width here. Okay, so is this point or this point or this point the largest? Like you still kind of start to get lost track here. Okay, so the frequency resolution is worse in this case. Okay, so again, just look at the plot and the last one E. Okay, 15 millisecond Hamming window. You'll probably get a struggle in trying to identify the pitch. Okay, but if you look at this plot, right, it may tells you the form and structure. Okay, the smooth pitch contour structure. So basically, we smooth out the pitch. So all this variation are kind of gone. What's left is kind of the resonance structure of your vocal track. Okay, so again, it depends on whether you're trying to get all these things or you're trying to get that kind of overall shape of the spectrum. Depends on your application. By changing the Hamming window, length of the signal, okay, it'll show you complete different plots. Okay, so in reality, this is the type of plot we're working on. Okay, in mathematics, this is the plot we show everybody, right? And it gives you an intuition. Okay, but in reality, these are the signals that we work on, and these are very short segment. We have speech that concatenate all these signals throughout. Okay, and make it more complex. There's noise. There's all the ways that people are trying to talk. Okay, so all these plots will change a little bit different for everybody. Okay, so that's the reality. That's the speech signal we're working on. The tools that we have designed, they have certain property. We can look at the simulated data to get an understanding of the frequency resolution, time resolution by changing windowing function. It changes the actual spectrum you look at. That's the point I'm trying to get at. Okay, so that was male voice speech. Female voice speech, very similarly. Okay, this is a signal R. Okay, local pitch period 200 hertz. Okay, again 30 millisecond, 15 millisecond rectangular window or Hamming window. Okay, B and D. This is rectangular Hamming window. It seems to point into the same peak of 200 hertz, which are okay. Okay. So the larger the original hertz is, that means given the same duration of the segment of your window, you look at more pitch period, you're actually more clean, right? Compared to the male speech. Because male speech, its hertz is much lower. Okay, that means it takes a long time to oscillate once. Okay, so if you're looking at a fixed segment, it oscillates not as much, okay, within a male speech. But female speech, it oscillates a little more. So if you're trying to find the fundamental frequency from the spectrum, female speech within the same segments of the sound, it actually will be able to pick out the fundamental frequency better. Okay, so again, the choice of N really changes a lot. That's what I'm saying. Okay, and it should be adaptive, but nobody's doing adaptive. Okay, because it's too hard of implementation. Practically, people just pick and use. Okay, 15 millisecond, 30 millisecond, pick it and shoot and use it. Okay, but as you know, right, depending on its male, females, voice, speech. Okay, what type of window function, you're gonna show different stuff. Okay? Again, a longer thing you see the spectrum. Okay? The shorter thing you see this kind of filter variation. Okay? Shorter variation. That's the sound. Okay. If you look at the unvoiced speech, okay, we know fundamental frequency only exists for voice speech. Okay. For unvoiced speech, right, something like this. Okay. You can do the same thing. Okay, but you're practically gonna see very difficult. You don't see those harmonic structure anymore. Okay? You don't see those repeated peaks. More or less, flat. Okay, because they are pretty much noise structures. Okay, you still some variation, but a lot of them, these are very, you don't know, is there really periodicity, is there an actual frequency component within the signal? It's very hard to tell. Okay, again, that's because some of the voice sound, it naturally doesn't have that periodicity. Okay, so what's also important here is to realize, okay, if you just do any, whatever method you do to extract fundamental frequency, okay, if you extract it over a speech segment, okay, you have to know some tools do extrapolation. Okay, even on the unvoiced speech, they'll give you a value. Okay, but in reality, there's no value. It's extrapolating a value for you. Okay, it's generating a value for you on those unvoiced sound. But in reality, for unvoiced sound, okay, those shouldn't have pitch values. Okay, some pitch toolbox, okay, extracting toolbox will tell you, okay, if there's no voice speech, I will give you a no. Okay, or if some toolbox will help you to say, okay, if there's no pitch value, I'll take these two voice and then draw a line and give you another value so that you have a smooth curve. Okay, so it depends on the toolbox design, and that's why I say nowadays it's very easy to fire up any toolbox to do things. Okay, what you probably need to understand is, if you use certain toolbox to extract pitch, okay, you have no pitch is only extractable on voice speech. Okay, because of the source and filter model we know about speech production. When you look at your speech, the toolbox, and for the segments of the voice speech, it also has values. You have to look into a toolbox to see, okay, whether it helps you to, artificially sort of, extrapolate some values or not. Okay, so it's kind of this kind of a practice. So just keep in mind, okay. I think this is important because too many toolboxes out there can do things, and they all do a little bit different stuff. But under the basic level, voice speech, unvoiced speech, source filter model, different length of N, okay, all this decides, okay, when you extract a certain feature, certain properties of that speech signal, is it extractable, or is it that extractable to a certain extent of whether it has resolution, it has the resolution we want, okay, or it has a resolution that's not enough, and you get those frequencies. So by simply choosing different ends windowing function, changes completely. These are all the same signal. That's what I'm saying. These are all the same signal. It's just different parameter you choose to extract the final value. So, okay, let me move on. In terms of short time synthesis, I'll go through this part a little bit quicker. Okay, it is not as important, but you might still want to know a little bit about when we do forward, right, taking the short segment, okay, then do Fourier transform. Okay, now once we have the Fourier transform, how we come back to the original signal? Okay, so that's called the short time synthesis. Okay, so taking the Fourier transform, that's analysis. Okay, taking back to the time domain, that's a synthesis, short time synthesis. All right, so how can we cover the original signal xn from the sample xn e to the j omega? Always called sample because essentially you take a segment out, get the take a segment out of the signal to a Fourier transform, right? Originally, you should have original signal is Fourier transform, but you pick a segment out, pick a segment out, pick a segment out to a Fourier transform. How we put all this pick a segment out of the short time Fourier transform back to the original signal? Okay, so for that sample xn e to the j omega. Okay. Okay, simple. First, let's do a filter bank summation of output signal. It's a sum of signal from each band of filter bank translated to the original signal. So again, just take xn e to a j omega, e to a j omega, HKN, right? This is the standard equations for resynthesis, right? And this is just that short time window segments Fourier transform. Okay. So and then just add up the values, right? K from 0 to n minus 1, you get y of n. Okay, let's do what we call another thing is called the overlap and add method. Okay, you have window segment, right? Spaced by R samples, right? Every window segment, you do a slide, right? R samples to another slide, R sample to another slide, R samples. Window segment spreading by R samples in time and overlapped and added to produce a reconstruction signal. Again, R from minus infinity to infinity, 1 divided by n, k from 0 to n minus 1, yr. What's yr? Is just basically xr. Okay, that signal of that part, then slide every r to get another xr, r e to j omega k. Slide another r, you have another xr, r e to j omega k. Okay. And sum over all of those things added. Okay, and for each r, for each r you slide, right, you can add back r slide back, add it back, and finally get back to the original y of n. All right, let's look at the filter bank summation equation first. So xn e to j omega we know equals e to j omega k sum from minus infinity to infinity xn minus n wk n e to j omega k n. Or we can rewrite them as wn xn minus n e to n minus j omega n minus n. Right. Okay. We can think about that as this thing as h of k wk n e to n minus j omega. Okay. So as you have, if you look at this is essentially some bandpass filter because wk is a windowing function. Windowing function, if you look at that. It's like a delta function around the lower frequency, right? So it's like a low pass filters get shifted to some location of WK. Okay, so you can think about this process. WK and e to j omega k n is just a impulse response of h of k, which is this is a low pass filter. Okay, that's what is called smoothing. Okay, because that delta function is like a low pass filter, right? So that smoothing being shifted to some frequency component. Okay, so y k of n equals to e to j omega k xn e to j omega, and we know that equals to from minus infinity to infinity xn minus n hk of n. So that's the filter bank summation equation. So your xn goes to h of k of n. Okay, multiplied by this, you'll get xn, right? This is your real signal. Okay. Multiplied by a shifted in frequency low pass filter, which is your short time window. Okay, you multiply by e to minus omega, then you get the short time dependent Fourier transform. Multiply by the e to j omega, then you back to the yk. Okay, the original signal in that particular segment. Okay, and repeat. Signal goes through some low pass filter shifted with respect to different k frequency. K indicate different frequencies. Okay. Multiplied by the e to minus j omega k, get the actual short time dependent Fourier transform. Okay. Then you multiply by the e to j omega k for all the k's back. You get your original signal y of k. Okay. So call that h delta k. That's filter bank summation. Can do an inverse of yk from this kind of idea of filter bank summation. Or overlap and method. Assume yr e to the j omega equals xr r e to the j omega k. Okay, where r is the integer indicate the frame, r is the windowing rate. Okay, and the k is basically the frequency domain sampling, right? So again, sampling around the 2 by. Okay, to reconstruct the signal, okay, inverse transform yr e to j omega is calculated for each r, right? So for each r, okay, you do an inverse transform and you sum over all r, get the original yn back, right? So again, repeat, right? Yn is xr r e to j omega, okay, where r is the integer, okay, indicate which frame, r is the windowing rate. Every a window of every say 5 samples, that's a windowing rate, right? Then that's your windowing rate. K is a frequency domain. So you can look at inverse transform of this, right? For each of the frame, right? You add up each of the frame, then you can get back to y of n. in each one of this, right, it's just this. Right? So basically, what you're essentially is taking the Fourier transform, time dependent Fourier transform, and keep adding, overlap and add, right? Overlap, add through the all segments to get back the original y over n. Okay, so mathematical form looks complicated. It's just simply your signal keep adding back and adding back. Okay, so repeat. Okay, so summary. We do a lot more analysis here. So, but analysis is assume you have L point window, assume R is your windowing rate, so you have L minus R, okay, sample overlap. To obtain a windowing segment YR of M equals to WR multiplied by capital R, okay, minus M times XM. This has L points. Every R is a shift, right? So again, every R is a shift. You get every Y R of M. Okay, shift R, shift capital R. Every frame it has L points. Okay, to generate a sequence called Y1 of M, Y2 of N for each of the frame, right? So now to obtain N that's greater than or equal to L points FFT to appropriate zero padding. Okay, you want to make sure it has at least N points and two FFT to get the points that you get YR to the J omega K, right? So the points you choose, right? The endpoint LP decides how many points you break W into. If you take 128, that means you're breaking 2 pi into 128 points. Your K will go from 1 to 128, right? So the endpoint L FFT decides on how many points you have sample around this unit circle. Okay, so that also equals to original length that we're actually sending into FFT. Again, these are all things that you probably learn the best, but it doesn't connect yet. But think about it. Okay, so take a windowing segment, do FFT. You essentially are doing a sampling around the unit circle. Okay, if you want to sample more, what you do zero pad. Okay, you zero pad your original signal. So take the segment out, zero pad it. Okay, then you perform FFT. Then you have endpoints FFT. Then you generate this YR to the J omega K. Now to resynthesize back, this is how you get short-term time-dependent Fourier transform. Resynthesize it back for every R, okay, between two consecutive frames, okay, there are endpoints in between, and do an endpoint inverse FFT, and then add it back, and add it back, and then finally you get back to the original signal. Okay, so very simple. Okay, this is analysis equation. This is how we actually come back from the Fourier transform. Okay, so to show time-dependent Fourier transform back to the original signal. Okay, so that's the synthesis part. The synthesis is not the voice synthesis, it's the Fourier synthesis. Okay, going forward to Fourier domain and backwards. Okay, back to the time domain. The trick here is not only because we have a time-dependent process here, we actually take a small segment out. So that particular mathematical equation of taking a small segment out and do a Fourier transform, it has both sides of the interpretation. One is really a short segment of a window sequence, okay, to do Fourier transform, or is a filtered operations on original signal. Can be viewed these two different. Okay, and why is it filter view? Okay, again, so that your mind be flexible a little bit, right? So because that windowing function by itself is a low pass filter. Okay, a low pass filter times e to j omega, it gets shifted to a different position. So it's when you have the original signal with that low pass filter, it is a smooth operation. Like smooth meaning it's going to kill out some of the high frequency component. So again, these are some of the same mathematical equation interpreted from different ways of looking at the same mathematical equation. Okay? But for the purpose of speech processing, I think what's the key point is the analysis part, okay, where you take a short segment out. What you really need to understand is that taking that short segment out changes the properties of that short segment. And the reason of changing is because of the choice of the windowing function, the length of the windowing function. The structure you're going to see after you apply the short segment doing a Fourier analysis and plot it. Okay, when plotted the different, we have seen those four different plots. Why you see those four different plots? Because the way we human produces speech, we have the source exciting a tube. Okay, that filter source exciting a filter function, okay, which is a resonant structure. source is a impulse train that, say your fundamental frequency 100 hertz, 200 hertz, 400 hertz, and those harmonics. Those things get filtered by your vocal tract making the sound. So if you plot your signal, the acoustic signal that you record at the microphone, okay, then you choose different length of the segment and apply different windowing function, you're going to see a different frequency structure of that signal related to either the source or the vocal tract. Okay, and another thing we didn't talk about here, right, is, I'll leave that out for others, is the microphone itself, right? The microphone doesn't have a flat frequency response. It has a certain frequency roll of certain things. So the thing you record here, okay, not the same thing as you record here. And you further do a short segment. So to be honest, the signal that you're processing is that the signal that you're actually sending out from your lung. Not quite. Okay, so we don't have to worry about, I'm saying a little deep fake. But 20 years ago, the things we're analyzing, and none of them are real signal, right? These are the signal that we have done so much processing to it that doesn't actually become the actual original signal you're really computing, right? So, but anyway, that's a side story. But just remember, all these components, essentially, we're approximating all stuff, right? The things we finally get, that waveform you see, is through all this processing, and then you get it, and you do a short-term processing, and then try to say, hey, I think your pitch, your fundamental frequency is 100 hertz. Hey, I think your resonant frequency of your odd is at 400 hertz. But you have done already so much across all this processing. Okay, so many speech analysis tools are basically designing all these processing tools to either analyze or to actually make sure, okay, the processing done here, okay, have minimum effect to the property you want to actually extract from human speech. Okay, so that's another key point I want to stress here. Okay. So anyways, short-term Fourier transform applications, basically the standard ways people do is trying to come up with, we call it spectrogram. Spectrogram is just time frequency representation of your short-time process, short-time Fourier transform, right? On the x-axis is your time, y-axis is your magnitude. Okay, so frequency in y-axis, time in x-axis. Okay, there are two type of processing spectrogram. One is wideband or wide analysis bandwidth, right? Wideband processing, wideband spectrogram, or narrowband spectrogram. Okay, now you know. Okay, wideband meaning the name is width, bandwidth is wide. Okay, it means maybe across 300 hertz. Band lobe is big. When you have band lobe is big, that means your time segment is small. Okay, so when people say I'm doing a wideband analysis on my signal, they're doing a short segment analysis of their signal. If people are saying I'm doing narrowband analysis on my signal, but they're saying they're doing a longer time segment on their analysis and on their analysis signal, because that wideband narrowband corresponds to the main lobe width of the signal you actually use. That's basically critically decided by the number of points you take it to do FFT. So wideband, good temporal resolution, of course, because they're short in time. Okay, high frequency contents is easy to do forward tracking because the segment is small. The only thing that can result is those signal parts that are high frequency, because they oscillate enough times within a short segment. So you can try to resolve those higher frequency components. In terms of speech, the format, the vocal tract portions of things are higher frequency. If you do a wideband analysis, it's easier to get format frequencies. Okay. So you'll see vertical stripes in spectrogram. Okay, windows aligned with the pitch period. If you do a narrowband analysis, we call it narrow analysis. Okay, longer time duration, you have a good frequency resolution. You receive more of the pitch and pitch harmonics, because pitch is, compared to formats, is much lower frequency. If you look at a longer duration, it has a lot more of those oscillations it can pick up and actually present. Okay, so you don't see vertical stripes, you'll see very horizontal kind of a stripes. All right, there we go. Here's a classical. Here's a data. Okay, frequency. Okay, time. Okay, here they use number of window 256 overlap 32 points. Okay, 124 points at FFT. Okay, so to plot this, you get kind of this vertical stripes across time. Okay. if you lower that number of window to 64 points, okay, so what you get now is a wideband analysis. Okay, so you don't see those horizontal stripes. Okay, because the horizontal stripes originally are like a fundamental frequency and its harmonics. Okay, basically some oscillation sets, that's periodic oscillation in anything that's slowlier. Okay. But if you take the window to be shorter, then you start to see more of this kind of stuff. Okay, so this kind of stuff. So they're not harmonics anymore. They're some of this higher frequency stuff. Okay, and what are some of the higher frequency stuff within this signal that get picked up here? Okay, so by lowering the windowing function, by lowering the number of points used in your windowing function, you go from narrowband analysis to wideband analysis. Okay, narrowband and wideband you can clearly see from the plot. One has this horizontal kind of stripes. Okay, one is just kind of this overall shape of things that's happening. All right, so here again, if you take window length to even wider, okay, then you get even more stripe, but you start to lose the temporal resolution, right? Because compare this plot to this one, right? At least you kind of know where these things happen. These things happen. Things have changed here. If you look at here, right? That temporal resolution is completely gone. Okay, so the longer the segment you get, of course, it seems to be more precise. This coloring. Okay, you see more coloring is more distinct, but what's happening across the signal seems to be gone. Okay, so not knowing where things have actually happened. Okay, the time resolution is a bad resolution. Okay. All right. Okay. Also depend on the number of overlaps. Okay, you can see other structures. Okay, let's look at a real thing. Right. This is an actual spectrogram of a speech sound. It's called every salt breeze come from the sea. And I don't know what's the best for you. Okay, so from the sea. It's wideband analysis, narrowband analysis. Okay, by taking the signal to a wideband, you see we call kind of the form and structure of this sound that's coming from the phonings of this synthesis. Narrowband analysis tells you, kind of the pitch and the pitch harmonic structures of this sound. So again, repeat. This is the actual sample of a speech sound. By taking it to wideband or narrowband analysis, you see two different characteristics of the speech sound. Right? They're all the same speech sound. In the wideband or narrowband, one you can look at this. They're back in the day, they're speech researchers by looking at wideband analysis. They actually know which word has been spoken, right? Because it's related to your vocal tract. Okay, vocal tract relates to the actual distinctive sound. This is more harmonic structure, right? So all these things look somewhat similar, okay, because they are coming from the same person, right? So speaking different sentences, different word, then you see a different words showed up as a different form and structures. Okay. So that's just an example. Let's look at STFT. We can use STFT also as a pitch extractor. Okay, this is one version. Okay, we talked about last time I talked about the Sonti pitch extractor. Okay, here just another version of a pitch extractor we call harmonic product spectrogram. Okay. So again, you take FFTs. Okay, then it has to do narrowband. Okay, the fundamental frequency, the multiples of fundamental frequencies are there. So what you can do is do downsample. You do downsample. Once you downsample your FFTs, okay, you again shrink the axis. You shrink the frequency axis. You shrink the frequency axis, and you multiply through. Okay, and you multiply through the ones that gives you the largest number. Okay, that's where the fundamental frequency is. Makes sense, right? Because harmonics happens at every multiple integers of the fundamental frequency. As you downsample, okay, your frequency is basically shrinks. Okay, the spacing of them. Okay, that sort of periodic structure still remains the same. So then you multiply across all of them, and you eventually get one peak. Okay, so we call this harmonic product spectrum. Okay, by doing harmonics, downsampling, multiplying through, then you put the one that's highest peak, and you find frequency related to that gives you the fundamental frequency. Okay, there's another way to do pitch extraction. Okay, we talk about one way to do autocorrelation, do pitch extraction. Okay, find a peak by shifting yourself across different lag and then find where that peak is, kill off the middle, and do peak picking. Here you can say, okay, let's take a signal, do FFT, do different downsampling, and then multiply this harmonic spectrum out. Okay, and the one that's the largest point will give you the fundamental frequency. Okay. All right, I want to conclude the frequency part last thing by looking at we call the issue on sampling. Okay. So let's actually answer this question. What should the sampling rate be in both time and frequency to provide an alias version of xn e to the j omega such that the original xn can be recovered completely? Right? That's first look at the linear filter interpretation of STFT. Okay, so xn, right, the time dependent Fourier transform equals to Wm convolving with xm e to the minus j omega n. Okay, so it's a linear filtering interpretations of xn, right? So some windowing function convolving with the signal. Okay. So a to j omega n can also be basically written basically Wm x n minus m e to the j omega n. Same thing. Okay. Right. So what you have is xn to the j omega equals to x e to the j theta plus omega because you shift, right? You shift your signal to a theta point, okay, here, theta point, and then w e to the j theta, right? So this should be, I think it should be theta. Okay. So that's your xn e to the j omega. So output frequency response is constrained by the spectrum of the windowing function. So let's look at both sides of the sampling. Time domain sampling. In practice, every window has a effective bandwidth b hertz. Okay. So that frequency constraint, frequency is constrained. So output has beta hertz. Recall that main lobe stuff. Half of the main lobe width is what we call the effective bandwidth. Okay, based on the Nyquist sampling theorem, right, xn e to the j omega needs to be sampled at least 2 beta samples per second, okay, to be able to completely fully reconstruct, right? So an example, right, Hamming window, okay, the main lobe width is WB, okay, equals to 4 pi divided by NL, which is the length of the segments. Your FB, okay, is basically 2 Fs divided by NL. F is your original sampling frequency, okay, divided by NL, which is the length of the segment. So if the original signal is sampled at 10 kilohertz, that's your Fs. Window length, if it's 100 samples, then your xn e to the j omega needs to be sampled at least 400 samples per second, right? 2 times FB to be able to faithfully recover what's originally to be recovered in the original signal that's been sampled at 10 kilohertz. Okay, so again, that's on the time aspect. The frequency domain, right? Xn e to the j omega, we know is periodic with 2 pi at your period. Right, you find a finite set of frequency n because you sample around endpoints such that we can faithfully reconstruct xn. Right, wk is not continuous; it's actually finite, discrete. Right, so wk equals 2 pi k divided by n. K goes from 0 to n minus 1. We call those n DFT representation. Right, you're sampling around the digital frequency of the unit circle. So from DFT theory, we know finite duration of signal of length t. Okay, that DFT needs to be at least n point sampling around the unit circle, right? So if your original signal is n points, okay, your DFT needs to have at least n points to split that 2k to be able to fully reconstruct the endpoints of your original signal. That we know. Okay, so need to sample frequency at least n points within that 2 pi. So 100 samples, and in time domain, you need to at least 100 samples around 2 pi circle in the frequency. Okay. So let's put it together. Okay. So find a total number of samples xn e to the j omega per second to give an alias representation of xn. Right. In time domain, we know at least 2 beta samples per second. Okay, because if it's not, then you start to repeat and then you count alias. Okay, 2 pi samples per second. E corresponds to the first node of the windowing function, the first point where the windowing function has 0. In frequency domain, we need at least NL samples. Okay, if your segment is NL samples in the frequency, whatever that sampling, WK, split that WK 2 pi into WK, that K needs to have at least NL points. So NL really corresponds, so we need to have at least NL samples. So NL corresponds to the length of the window. Okay, so total sample rate is 2 beta times NL. Okay, samples per second. Okay, for most window, this beta, which is the bandwidth, the effective bandwidth, basically half of the window width is some C, some constant, some value multiplied by Fs divided by NL hertz. Okay, so C is some proportionality constant, depends on different window. It has a different constant. Okay, and some proportional constant, like for example, rectangular window versus Hamming window is just one of them. Is twice of the other, right? So the proportional constant one is twice of the other one. So for most window, beta is some version of constant, okay, multiplied by the original sampling frequency divided by the actual NL samples you have. So Fs is the sampling rate of the xn, NL is the window rate. So xn e to the j omega needs to be at this 2 beta NL, right? Now you put it together basically 2C Fs. Okay. So this 2C, okay, are some oversampling, we call it oversampling ratio, depending on your windowing choice. Okay, it has a different this proportion constant. Okay, so at least 2 times Fs. Okay, right? That's already that's Nyquist theorem. Any signal you have at least twice the highest frequency exists in your signal, and also because of windowing function will introduce other things, you want to make sure you additionally multiply by other constants. So to be able to fully reconstruct the XML from the time-dependent Fourier transform. Okay. In practice, you usually are not aware of this thing. Okay. What you do is just do it, and then take a windowing segment, let FFT be long enough, and then things are okay. But to work out the real math here is think about windowing function, because that delta shape kind of function, it effectively constrains the output of the signal. Okay, right? So that delta function, the effective bandwidth is how much frequency will it let through. Okay, so if you want to fully reconstruct the original frequency, okay, of the original signal, you want to make sure that effective bandwidth is at least twice as much as your original xn. Otherwise, you're gonna have an alias version of that. So I need to have at least twice of that thing, and depends on, again, work out this thing, the samples in the frequency domain, to make sure the original time domain signal can be fully reconstructed. Put it all together, the xn e to the j omega, within them it needs to be at least 2 CFS, which is your sampling rate. Okay. All right. So let me conclude a little bit, and we'll stop here. Okay. So the frequency analysis. Repeat. I think a lot of them, in practical sense, you might not be aware. Okay, when you do an speech analysis in terms of frequency, but I think it's important to go through. For example, this 1, 2, 3, right? The 3 pages, right? When you go through these 3 pages, looking at 12 different plots, and you understand why you're seeing the plot you're seeing. They all come from the same signal. Okay. That's basically what this section is meant for you to know. Okay, so understanding by choosing a different windowing function, understanding by choosing the NL points. Okay, it changes the things that you see on the spectrogram. Okay, and you want to analyze the frequency, right? For example, if you use this, right? If you've done the same signal, just because your choice of Hamming, your choice of rectangular window, choice of the length of the segment, you get some different output, and maybe you use this as your features for other things, right? You choose this thing, this becomes your feature. If you choose this thing, this becomes your feature, okay, to do whatever recognition, machine learning, AI work that you're trying to do. At this point, you already lose a lot of stuff, right, compared to here. You're looking at different properties of the signal, and you send it out for the system to try to analyze or to recognize or to do things on. Okay, so make sure these are very fundamental building blocks that even changing there, okay, change things. Okay, and the reason you have to come back, okay, repeat several lectures like this speech production, source and filter model. basic knowledge of we as human producing speech. Okay, when we changes the windowing function, when we changes the window name, then combined with all the FFT and signal system idea that you guys have learned in undergrad. Okay, these two start to combine and understand. Okay, for males, voice speech, female voice speech, okay, voice speech. This when we are looking at the output, which is a source exciting a filter, become our speech, looking at different segment, different length. If it's male or female, okay, then we will see different properties, same signal. Okay, so I think these are very critical. Okay, to understand. Okay, because as we move later and later, people start to make it even more complex to derive different features from the speech signal, right? You start to lose the idea of why MFCC people just start with 30 millisecond timing window, right? It's almost no-brainer. Like if you look at any toolbar, it's always starting 30 to 40 millisecond, 50% overlap, timing window, compute MFCC. Okay, even that particular choice. Okay, that means you are choosing this one. Okay, not this one, and not this one, not this one. Okay, so that's that's a critical choice that you make whenever you do any analysis on speech signal. And because this speech signal has so much information within them that you have to be aware which segment or which things you use to write. And then hopefully also for me personally, when I start learning speech processing, I go back and kind of revisit my DSP because it becomes rusty. So I feel like okay, I didn't really get what was happening in my signaling system until I hit an application like speech where there's so many layers of stuff that actually depend on you kind of already know that that's a linear filter interpretation. That's a convolution writing. Okay, stuff like that. So that's the point when I actually start also revisit back some of the terminology and sampling as well. I never really get what sampling is really about until I started to hit some of these ideas. Okay, so this is an important concept to also if you feel like it's not quite clear, maybe go back to some DSP signal system kind of lectures and you'll refresh your memory. They are very similar. Because we're gonna continue on. Okay, it's gonna get even more a little bit more complicated later on. Okay, so the next class I'll stop here quickly. So the next time I'll talk about particular model called the linear prediction model. Okay, so that's a very nice model. Here we only have provided tools for analysis, right? We talk about computing zero crossing, computing energy, computing all these things. Okay, we talk about computing wideband, narrowband spectrogram. Okay, these are analysis tools to analyze the speech sound. Okay. Next step, we're going to start using zero crossing tools to model the speech sound. Okay, we can assume. Okay, we can assume now really trying to take this source and filter model into a set of parameters. Okay, so we can say source exciting a filter. Okay, that filter is a all-pole model. Okay, now let's try to find the all-pole model's coefficient. Okay, now we then become a modeling work. Okay, trying to model the speech sound in terms of this source and filter operation, and that can be all cast as a problem of linear prediction. Okay, we'll talk about that. Okay, and then that's also very. I think it will go. Once you get that linear prediction, then the next step we'll talk about basically feature extraction. Okay, then the machine learning kind of idea will come in and say, okay, once you can start model stuff, then you can extract parameters, then you can extract representation. You can say, okay, having all these parameters, I can describe the filter. Then that means I can extract features representing filters. Okay, right? Then that becomes a feature extraction approach. Okay, so we'll talk about linear prediction as a model, trying to say, okay, I have a time sequence of speech sound. How do I model that as an all-pole time series model? Okay, all-pole time series model has parameters. Okay, understand how we derive those parameters, the reason why, and then what kind of effect that by using the all-pole model, what can we do? Okay. Once you have that, right, the next step will be, okay, now you can represent the speech sound. The filter part of things become some parameters. That means every frame can extract certain numbers of parameters, and that when we call that, that's called feature extraction. Okay. Then we'll talk about different ways of doing feature extraction. Then later we'll talk about the machine learning part. So the sort of solely progress. So make sure each layers of tools, you should have a clear understanding with respect to speech. Okay, I don't expect everybody knows everything about DSPs and all these things, but you should know its relationship to speech sound, its relationship to speech productions. OK， 好，我们今天先讲这。